Hello, everyone. My name is Hassan Yunus. I am the Ashrae Falcon Chapter President. Welcome to this very special webinar where we are hosting Ashrae's President-elect, Mick Schwedler. Mick has been working with Trane since before I was born, 1 year before I was born, 1982. He holds many patents. He was the chair of Ashrae 90.1. He also chaired the AEDG Advanced Energy Design Guide Steering Committee. So we are into a very interesting presentation. We're going to be talking about high-performance water systems. This webinar has been organized by many chapters. It was mainly organized by the Chandigarh chapter in association with the Mumbai chapter and Falcon chapter. I want to thank all the members in these chapters and especially the committee members from CTTC that have made this possible. Without further ado, I'll hand it over now to Manikhana, who will have a few words and a presentation on RP. Thank you and good luck to everyone.
Yeah, thank you, Mr. Yunus, for your great introduction. So welcome you all, and good afternoon, good evening, and good morning to everyone who all are attending today's session. So this is a great session. I'm sure you will definitely like it. And this is one such initiative by Ashrae Chandigarh chapter in association with Ashrae Falcon chapter, Ashrae Mumbai chapter, and RATA, the Refrigeration and Air Conditioning Traders Association Limited from India. So yes, this is the today's session, which is on high performance chilled water system. So before directly jumping to the topic, I'll just like to brief you about Ashrae. I'm sure you all are aware about Ashrae. Ashrae is American Society of Heating, Refrigerating, and Air Conditioning Engineers. So it is a society which is working with the engineering professionals. So it is an American professional association seeking to advance heating, ventilation, air conditioning, and refrigeration systems design and construction. Ashrae has more than 57,000 members in more than 132 countries worldwide. Its members are composed of building services engineers, architects, mechanical contractors, building owners, equipment manufacturers, employees, and other concerned with the design and construction of HVAC systems in the buildings. The society funds research projects, offers continuing education programs, and develops and publish technical standards to improve building services engineering, energy efficiency, indoor air quality, and sustainable development. So yes, I'm sure you all are member of Ashrae. If you are not, you can log into join.ashrae.org and become a member of Ashrae today. So yes, here's a theme for Ashrae Society Year 2020-2021. The theme for this year is Ashrae Digital Lighthouse and Industry 4.0. So this is the theme which is running by our Ashrae President, Mr. Charles Courage. So his theme focuses on reimagining the building industry and Ashrae's place in it by integrating not only industry segments, but also technology. Digital transformation is not only simply associated with adopting new technical solutions. Knowledge needs to be captured and linked in such a way that all relevant stakeholders benefit. Doing so requires understanding of how to collect, store, and analyze data so that it is insightful and actionable. So this is a great theme, and I'm sure we all are connecting through this virtual presentation and through digital means of connecting and networking and learning this opportunity. This is one such kind for this year's presidential theme. So there is another unique portal which is running by this year, and this is under the society's theme, which is the Ashrae's Digital Lighthouse and this Industry 4.0. So there are few sections that have been developed. So here's the link that is shown on your website. This is the section which is under technical committees, publication and standards, education, certification, and external resources. These are all being showcased on the Ashrae online website. So it's a great knowledge sharing platform, knowledge sharing portal, which connects you through worldwide with HVAC&R and the building professionals. So this is a membership campaign which is running by Ashrae Chandigarh chapter. So Ashrae, the theme, join and be a part of more than 125 years professional technical organization. So join us, and there is no much fees, and you can say it is already subsidized for the developing economies. So Ashrae Chandigarh chapter and Ashrae basically India country is one of the underdeveloping economies, and the membership benefits and the membership fees, which you can see on your screen. I must encourage all of the attendees of today's webinar to join Ashrae and to get benefits which are abundant in nature. I'm sure you all will get more benefits once you join Ashrae. So here's a today's webinar topic, which is high performance chilled water systems. So it is already being announced, organized by Ashrae Chandigarh chapter in association with Ashrae Falcon, Ashrae Mumbai, and Rata Association, which is us. So I must encourage before all of the meetings, before all of the Ashrae webinars, we must go through this Ashrae Code of Ethics. In this and all other Ashrae meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall all avoid all real or perceived conflicts of interest. So this is our code of ethics, which we must run. So now I would like to invite Mr. Anuj from Ashrae Chandigarh chapter to speak on Ashrae research for research promotion.
Thank you, Mani, and good evening once again to all of you. I am Anuj, and I am heading the Ashrae Research Promotion Committee of Chandigarh chapter. I also welcome my friends from Ashrae Falcon chapter and President-elect. Ashrae, as you know, is a very well accepted organization worldwide, which has about 125 years and have set a lot of standards. And for doing so, there's a lot of research which is required, which is to be done. So for doing this research, it is very important that we need some contribution from our members and non-members also, who can become members as advised by Mr. Mani. And we have various levels of contribution, which starts from as low as $100, which is around 7,500 rupees in Indian rupees. For last 10 years, this campaign has been started, which is known as Research Promotion Campaign, which is to support the endowment research in Ashrae Foundation, Young Engineers Foundation, Ashrae Scholarship. Ashrae gives a lot of scholarships to college students to do research and to come up with new ideas to enhance the quality of life. And this is the primary fund, which it raises around $2 million annually through worldwide campaign. And we are proud to be associated with Ashrae and contribute towards the development of newer technologies. As far as research promotion, anybody can donate. There is a form which you can see on the your right hand side of the screen, and you can donate your money for any of the things, whether it is for Ashrae research. There are two committees, which is Ashrae Research, which is a global, and then another is Ashrae Research Canada, which is for specific for Canada-based research programs. Then Ashrae Learning Institute of Education, then research. You can check any of those funds and total it and send it through electronic transfer. We do not take your CVV numbers. It is automatically done. Next slide, Mani, please. Now, Ashrae has been involved since 1919 and has supported research to improve the quality of life. As we all are aware that we do research in air conditioning, predominantly air conditioning and indoor air quality, sound, acoustics, duct design, thermal conductivity, weather data, smoke control, solar design, and host of other activities which are associated with building and built environment. So I would once again request all of you to please be part of this campaign and contribute to our society. Thank you.
Yeah, thank you very much, Mr. Anuj. And now I would like to invite Mr. Mick Schwedler. He is our today's speaker. So I would like to brief introduction. I'm sure you all are aware, being an Ashrae member and Ashrae non-member as well. So he is the president-elect currently, and Mick has been active in the development and support of HVAC systems for Trane since 1982. As an applications engineer, his areas of expertise include system optimization, as well as chilled water and water source heat pump systems design. Mick, currently holding position as president-elect in Ashrae, served as a treasurer, vice president, Director at Large on the Ashrae Board of Directors. He is an Ashrae Fellow, recipient of Ashrae's Exceptional Service, Distinguished Service, and Standards Achievement Awards, and was chair of SSPC 90.1 2010. Mick also served as chair of the Advanced Energy Design Guide Steering Committee and was on the project committees for 50% hospital and office buildings ADGs. So I would like to invite Mr. Mick Schwedler for the great presentation today, and I'm sure everyone will have a great session, great learning session, and we all will capture many of the great things described by Mr. Mick. So over to you, please, Mr. Mick.
Thank you very much, and good evening to everybody. As we get my presentation up here, we want to make sure that we thank the Chandigarh, the Mumbai, and the Falcon chapters for hosting, and we welcome all of our guests today. Osama, can you please confirm that the presentation screen is showing?
Yes.
Wonderful. Today we're going to talk about high performance chilled water systems, and it's very appropriate that given President Gulledge's presidential theme and society theme this year on technology, this could not be happening without the technology that we have today. And there's so much we can do within our building systems from a technology standpoint. We also want to share that this has not come to people free, but this is done through what Ashrae calls a distinguished lecturer program. And that program is to bring presenters from all over the world to our chapters, and therefore to both members of those chapters and also to future members of those chapters, those who are guests today and joining us today, to show that we have a global influence and we can learn from people all over the world. And there are distinguished lecturers from all over the world, including India and the Falcon chapter in Dubai. As you become involved in Ashrae, what I tell people is, if you have a passion for doing something within our industry, there is a place for you within Ashrae. There are fabulous ways to serve. There are ways to volunteer. And I have always found that when I volunteered, sometimes it seemed like I was giving more than I received back at that particular time. But in total, I always received back more than the time I volunteered and the effort I gave in volunteering. Our course description was shared, so we're not going to spend time on that. We do have, there are continuing education units available if people need those for any licensing, and that can be done. Also, if somebody is an architect, these are registered for architectural credits also to maintain that license. We're also a partner with the U.S. Green Building Council, and I imagine the India Green Building Council, and these are available for those who are lead APs and need credentialing for that, and this is available for 1 credit hour. Our learning objectives today are all around chilled water systems. We're going to talk about design today versus design that was done in the past. How can we do better than people did in the past, than project teams and engineers, and how can we improve on the decisions that people made in the past? How can we look at our systems and use the new technologies available today to make our systems more sustainable, simpler, more efficient moving forward in the future? And we're going to talk about controls, because once a system's installed, we really need to make sure that it's controlled well, so it's operable, it continues to operate, and it's sustainable not just for a year, but over the entire life of that building. But before we can talk about high performance chilled water systems, we need to start out with what's normal performance. As was mentioned, I began my work in the industry in 1982, and that was before all of our hosts today were born. That's happening more. But in 1982, the pinnacle of chilled water systems was a design called the primary-secondary system, or the decoupled system. In a primary-secondary system, we have a chiller and we have a pump per chiller. The flow through the chillers is constant through their evaporators. We have two-way valves out in the system, and those two-way valves modulate and change the water flow not only through the valves, but also through the system. These secondary pumps, or distribution pumps, have variable speed drives, and those variable speed drives change their speed, save pumping power when the valves close. Well, if we have constant flow through the chillers, but variable flow through the system, we need to have a way to make up the difference between that flow, and that's a bypass line, sometimes called a decoupler, since it decouples or separates the working pressures of the chiller pumps and the secondary pumps. This bypass line should not have obstructions in it. We don't need to control the flow rate. The water knows where to go by the operating pressures in the system. A question is, how are many systems designed? And many systems are designed today and have been for many years using the AHRI standards. Those are how chillers are rated. And there are some base or standard conditions, and those are shown here on our screen, the leaving chilled water temperature. And the important parts are the temperature differences. On the chilled water side, it's about 5.6, between 5 and 6 degrees C. On the condenser water side, it used to be a higher number because chillers weren't as efficient, but as chillers became more efficient, the delta T came down to just over 5 degrees C. So today, if we started with that as the basis of our normal chilled water systems, we're now going to look at what can we do to make them high performance. And we're going to use industry standards, not any particular companies or, for example, my opinion, but we're going to look at what the industry is saying. As we were doing research for this presentation, we looked back and we always wondered, where did that 5 or 6 degrees C delta T come from? It's been in the industry since at least the 1940s, and a person that I work with and I were going through some historical documents, and we actually found a newsletter from 1935. And in that newsletter, I will let you read what's in that newsletter. So the 10 degree delta T, 10 degree Fahrenheit delta T, which is 5.6 degrees C delta T, we've been using that for at least 85 years. And the question today is that the proper delta T using the technologies that we have today in order to design our systems? And when we look at what the industry is telling us, we should be using higher delta T's and lower flow rates in our systems. And we'll talk about why, but first we want to talk about what is the industry saying. Ashrae Standard 90.1, it's starting in 2016 and 2019, requires coils to be selected with at least a 15 degree delta T, which is 8.3 degrees C delta T. And that's higher than it was in the past. The Ashrae GreenGuides all recommend higher delta T's and lower flow rates, both on the chilled water side and the condenser water side. Steve Taylor, who's one of the foremost chilled water plant design experts in the world, wrote a series of 5 Ashrae journal articles. They're available to Ashrae members for free on the Ashrae technology portal. And in those articles, in his 3rd article, he talked about design parameters, and he also said, reduce the flow rates, increase the temperature differences. And Ashrae, either a year or 2 years ago, put together a new chilled water course, chilled water design course. And in that course, it says begin with a 14 degrees C delta T, which is a larger delta T than normal. So all of these entities, all of these industry recommendations are saying, let's have a higher temperature difference and a lower flow rate. This is the summary of Mr. Taylor's article from the 2011 December version of the Ashrae Journal. And there are a couple important points here. Not only is he saying the delta T should be larger, but he said a couple other things in the summary. And that is, this is true for office buildings and data centers. Now, why would he say that? If we think about the profiles and the cooling load profiles of data centers, they're constant. Once a data center is up and built, it has a constant load every hour of the year. Whereas office buildings change depending on the time of day. The load profile varies by season, particularly in a climate like ours. Not so much perhaps in India, but what Mr. Taylor was saying is that reducing the flow rates is good whether your loads are constant or they vary. So no matter the application, it makes sense. The second thing he said, there's often some claims made that this is only for one chiller manufacturer or a few chiller manufacturers. And Mr. Taylor got information from all the chiller manufacturers and found that no matter the chiller design, whether it's a screw chiller, a scroll chiller, a centrifugal chiller compressor, whether or not it has a variable speed drive, this makes sense. reducing the flow rates and increasing the delta T makes sense. As I stated, the Ashrae standard 90.1 2016 and 2019 require that 8.3 degrees C delta T and require our coils to be selected for that. Now, there are some exceptions, for example, little fan coils, but everything in the industry is telling us to go toward higher delta T's and lower flow rates. But as engineers, we now need to ask the question, why? What changed? And what's changed over the last, since about 1975, so over about the last 45 years, is what's changed is the efficiency of chillers. This is a graphic of the efficiency of chillers, the minimum requirements per Ashrae standard 90.1 over the years, and then what the best technology can deliver today. And we see that there's been a significant increase in the COP, and I really like that societies like yours and cultures like yours use the coefficient of performance. That is, how much useful cooling do we get out of the chiller compared to the work put into that chiller. In the US, we use what I tell people are the wrong units. We use kilowatts per ton, and that's not a good measure of chiller efficiency, but COP really is. And when we look at what COP has done to the efficiency of chillers, and these are just the required ones, the efficiency of chillers has increased by between 52 and 67% over the last 45 years. What's happened to the efficiency of pumps? The motors are a little bit more efficient. The pump providers, the pump manufacturers continue to improve their products. How about cooling towers? We use different fill. When I started, we used wood in cooling tower for the fill. Now we use some type of PVC. We have more research done, and we have more technology done to make sure that the cooling towers are more efficient. But even though the pumps and cooling towers are more efficient, there's no way they increase their efficiency by 50 to 70%. So that tells us perhaps there's something we should look at, and we should look at why and how this affects our system designs, and why the industry is telling us to use lower flow rates and higher delta T's. So let's walk through an example. This is an example, and I've tried to convert most of the slides here to SI units. I apologize if I got any units wrong, and I'll correct those if people point those out as we move forward. So this is a simple system design where we have a single chiller. We have the temperatures, flow rates, pressure drops shown on your screen. And what I tell people about the numbers on these screens is that they're wrong. Why are they wrong? Because they're not your job. They're not your specific application. There's no magic flow rate or magic delta T. But the flow rates we've used for the last 85 years are too high. The delta T's are too low. So this concept is true no matter your job, no matter the application. So let's look at how this system operates. So if we look at design conditions, of the normal performance chilled water systems, here's our chiller usage at full load, our chilled water pump, condenser water pump, and cooling tower fans. Now, if we followed the recommendations in the Ashrae GreenGuide and reduced our flow rates and increased the temperature difference, what we have to make sure we share the assumptions. And the assumptions for this first part are we're going to use the same coil. We'll talk about that in a few minutes. And we're going to use the same pipe sizes, so the pressure drops and pump power will go down. So as the flow is reduced, the pump power goes down. And also, since the pipes are the same size, the pressure drop goes down, so the pump power is reduced. The cooling tower we're going to use a cooling tower and resize that cooling tower using the same approach temperature. That is the same temperature difference between the leaving tower temperature and the outside air wet bulb temperature. When we do that and we've reduced the flow rate, the water temperature going to the cooling tower is higher, and therefore the cooling tower is a more effective heat exchanger. We can select a cooling tower that's between usually about 7 to 10% lower cost and lower fan horsepower. The chiller. When we do this with a chiller, we're going to use essentially the same chiller. However, if we're going to use the same coils, we have to send that coil colder water. Therefore, the chiller's leaving chilled water temperature must be lower, which means the chiller will use more power. On the tower side, on the condenser water side for the chiller, the leaving condenser water temperature and the entering tower temperature are higher. So again, the chiller power goes up. The chiller must use more power, but the cooling tower and the pumps use less power. So if we look at this from a system standpoint, from a cost standpoint, our pumps are smaller, less costly. Our cooling tower has reduced cost, and the chiller is the same cost unless the compressor size had to get larger. So this is a lower cost installed cost system. What happens to the power? So on the right is the Ashrae GreenGuide flow rates. And the first thing most people notice about that graphic is the chiller power went up. And I always like to ask the question when we're in face-to-face and in person, is that good or is that bad? And the answer is it doesn't matter. The reason it doesn't matter is because the building owner pays not for the chiller, he or she pays for the entire system for the entire building. Therefore, as long as the total comes down, it's beneficial to the building owner and it's beneficial for our environment. But this is at design conditions. What happens at part load conditions? As we reduce the loads, the cooling tower can make cooler water. The difference in chiller power comes down. And what we see is that the Ashrae GreenGuide flow system actually saves more energy at part load conditions than it does at full load conditions. In fact, if we look at it at different operating times during the year, we see that the savings are between about just under 4% to almost 16%. Now I tell people, be really careful when other people share percentages, because 16% seems like a lot, but remember that's when the system's operating at 25%, and that's going to be less power. But overall, from a yearly annual standpoint, the system energy usage is lower. And that's a great benefit, and that's why the Ashrae GreenGuide, Ashrae Standard 90.1, the Advanced Energy Design Guides, why the chilled water design course from Ashrae tells us to reduce the flow rates, because it saves energy from a system standpoint. Now, as a consulting engineer, as a building owner, as a contractor, you now have some decisions to make. As I stated before, the assumption was that we left the pipe sizes the same. When we leave the pipe sizes the same, the pump power goes down by a lot, and therefore the pump energy goes down by a lot. Another option is to reduce the pipe sizes. When we reduce the pipe sizes, we reduce the costs, and particularly if there are long piping runs or it's a large chilled water systems, those costs can be very large, and those savings can be very large. But we now have a decision to make. Do we keep the pipe sizes the same and save all the energy and energy costs? Or do we reduce the pipe sizes, reduce the first cost more, but not save as much energy? And that's always a decision that can be made by the project team for the specific application. There's a consulting engineer who wrote some articles on this a number of years ago, and they said they used some of the pipe, pump, and cooling tower savings to purchase a more efficient chiller. Because in the previous slides I've shared, we've used the same chiller. When we use some of the pipe costs, tower costs, and pump costs to put more money into that chiller, to put more copper, more heat transfer surface into that chiller, the difference between the old flow rates and the GreenGuide flow rates, the difference in chiller power gets reduced. So there are a lot of different analyses we can make in order to apply this on particular jobs. This is a graphic that I did not have time to change to SI units, but what this graphic shows is what the traditional pipe sizes would have been in different systems, and using the Ashrae GreenGuide, what the evaporator and the condenser water pipe sizes would be. So we can certainly see that there are the capabilities and there's the chance to reduce the installed cost, but that needs to be balanced against the energy usage of the system. Now, when we get to some large pipe sizes, sometimes we can reduce it by a factor of 2. And I've seen many project and design consulting engineers reduce the pipe size by a factor of 1. And that gives a good balance between the installed cost and the operating costs. And what this tells us is our lesson is take that most efficient part of the system. A chiller has a COP, a good chiller has a COP of around 7. If a pump is 70% efficient, its COP is 0.7. So a chiller is about 10 times more efficient than the pump. So let's work that most efficient part of the system a little bit harder. That's what the Ashrae GreenGuide tells us to do. Now, at this point, there are usually questions that come from the audience, and there are three primary questions. So let's work through those, and we will have time at the end of the presentation for questions from the audience. So please use the chat screen to send those questions, and Money will be coordinating those questions. So the first question is, does this work for everybody's chillers? Some people say, well, Mick works for a specific company that might be good for his company, but not others' companies. These are three documented jobs in industry journals. And the first one was an airport. It happened to be out in Boston. And when they reduced their flow rates, they reduced their pipe sizes. That reduced their installed costs by more than $400,000, and it reduced their operating costs. There was a large chemical manufacturer in one of the states in the US, and when they reduced their flow rates, they had a large built-up cooling tower. With that cooling tower, not only did they reduce the size of the cooling tower, but it had a concrete sump. And that concrete sump was able to be also be reduced. So not only did the cooling tower costs go down, but the cost for the sump went down. And I like to ask HVAC design teams, when was the last time we thought about the costs of concrete and excavation? But the building owner pays for that too. So let's make sure that we look at the entire cost advantages of this system. And again, that cost went down, as did the operating costs. There was a computer provider based in San Francisco, and they had a study done for them by the local utility. They used the existing pipes, or an existing tower, they reduced their pipe size, but their installed costs and their operating costs went down. These jobs were done by 3 different chiller providers. And as Mr. Taylor said, there is no difference. It works for single stage and 2-stage chillers. It doesn't matter who is providing the chiller. And if somebody says that this doesn't work, you're an engineer. Get the data, do the analysis, and you can show that you can reduce the installed costs and the operating costs in almost all systems. A second question, and this is one that really is a very valid question to ask. Can it work on existing systems in retrofit applications? And the answer is absolutely yes. Many people think that a coil is designed for a particular temperature difference and flow rate. It's not. It's selected there. I tell people coils are just dumb pieces of metal. They don't know anything. They don't know how to do anything. Their purpose is to transfer heat. When we give a coil colder water, it will use less of that water, and we will get the same heat transfer. Because a coil's flow rate, a coil's heat transfer is the U value times the area times the log mean temperature difference. And the cooling capacity is the flow rate times the temperature difference. So let's look at an actual coil selection. And this is an existing air handling coil. So the goal in this case was to deliver after the retrofit the same leaving air conditions and therefore the same load. In order to do that, the coil was reselected. Instead of using a 7-degree entering chilled water temperature, it uses a 5-degree C temperature. The flow rate goes down by about just under 40%. The leaving water temperature, when we look at how coil and how heat transfer works with that log mean temperature difference, when we reduce the inlet temperature to that coil, the outlet temperature will also go up because of how heat transfer works. Therefore, we can go from a 10, pardon me, this is degrees F, I didn't get this right, from a 6-degree C delta T to a 9-degree C delta T, and I'll correct that slide before I send it to Money to be posted on the chapter website. So the delta T goes up, but again, the chiller has to provide colder chilled water temperature. Now, one question people ask is, when doesn't this work? Well, it may not work on small fan coils that have only 2 or 3 rows, because with those reduced rows, there's reduced heat transfer area, and therefore the return water temperature follows the supply water temperature down. But on almost all air handling coils that are 6 to 8 rows, particularly those that have internal enhancements, this works extremely well. And we've seen many jobs use new colder chilled water temperatures and reduce their pumping power significantly using the existing coils. One other thing that you might have to do, sometimes coil control valves are oversized. And if the coil control valve was oversized when we had a 6-degree C delta T, it's going to be even more oversized at a 9-degree C delta T. So you might want to change and retrofit some of the valves on those coils to get better control at lower flow conditions. The third question is, does this work on the condenser water side too? And the answer is absolutely yes. Like a coil, a cooling tower is just a heat exchanger. If we give it warmer water, it can exchange more heat. So this is something I get to talk to building owners and consulting engineers about every 2 weeks. And when we do this, usually the owner turns to the engineer or vice versa and says, that's exactly our job. And so I'd be surprised if a number of people didn't have an application like this that they're working on today. And it is time to replace the chiller. The cooling tower is in good condition. It was refurbished a couple years ago, but our cooling needs have gone up. We're putting more people into the buildings. We're having more ventilation air. We have more data, more racks in our data center. And the condenser water pump and pipe are in good condition. And sometimes the pipe runs under a parking lot or something like that. They don't want to dig it up. But the first thought is we have to replace everything. We have to replace the chiller, the pipes, the pumps, the cooling towers, and the job becomes expensive and it goes out of budget. Well, we don't have to do that. By selecting the new chiller at the proper conditions, we can easily increase the heat rejection and therefore the cooling capacity provided by that chiller by 50%. Because we can use the same outside air, we can use this, we can use the same flow rate, the same design wet bulb temperature, and by having that higher delta T, we can use the same cooling tower. But what I tell people is this isn't free this time. Well, we have the same pipes and the same pumps and they're designed for a good condition. In this case, the condenser leaving water temperature went up significantly and the chiller power will go up more than it would on a new job. So you do have to balance this, but many times I've seen jobs come back into budget and be able to move forward because all we had to do was replace the chiller and select it at the proper conditions. The final question people ask is, does this work even if the piping runs are short? Because if the piping runs are short, the pressure drops aren't very high, the pump savings aren't as much. Well, what we did in this case is the bars on the left-hand side are the old flow rates. The bars on the right side are the Ashrae GreenGuide flow rates. And I told you there was a slide where we talked about the assumptions, and I told you the numbers were wrong because they assumed some particular pressure drops. So we said, well, if they're wrong, how wrong can they be? How low can the pressure drop be? Well, what if our pipes magically could give us a 0 pressure drop? Well, in that case, if the pipe gave us 0 pressure drop here at design conditions at 100% load, the system power would be a little bit higher because we will use more power on the chiller than we saved on the pumps and cooling towers. But even though at design conditions, the system power is higher at all off design conditions, the system is still more efficient. Therefore, this works even if the cooling tower is on the roof directly above the chilled water plant. We can save energy annually during the year by using lower flow rates and higher delta T's. So what I like to help people understand is that particularly in retrofit applications, you don't have to be confined or handcuffed by what the last designer or engineer did. You can use your knowledge and your experience to provide better value for the building owners. What we have to remember, though, is sometimes people will say, yes, but the chiller uses more power and it's the biggest motor in your system. And that's true, but that's not what the building owner pays for. The building owner pays for the entire system. And in that entire system, the energy use of that system goes down, and that's what the industry is telling us. So let's consider this for future applications, both new and retrofit. The next thing we're going to talk about is, we talked about the normal performance chilled water system is a primary secondary system. Let's look at variable primary flow systems. In a variable primary flow system, what happens is rather than having 2 sets of pumps, we only have 1 set of distribution pumps, and we vary flow not only through the coils, but also through the chiller evaporators. Now, what I tell people, this is a 90-minute seminar. We're going to do it in about 4.5 minutes because our audience today is much smarter than most audiences. But what we're really going to do, we're going to just hit on the highest points. What are the most important parts about variable primary flow systems? Another thing you'll notice in the system is the bypass line has a control valve. And this control valve's purpose is when the system flow rate starts to drop below the chiller's minimum flow rate, that control valve modulates open so that we always keep the flow through the chillers above their minimum flow rate. That gives us good heat transfer. It gives us good, reliable chill water leaving temperature control and good efficiency. Bill Bonfleth, who's an Ashrae presidential member and a research student of his, Eric Pyre, did research comparing systems that were originally designed using the old flow rates and changed to the Ashrae, or used primary secondary systems and changed to variable primary flow systems. And they found that the first cost goes down because we don't have 2 sets of pumps. We don't need the space for the pumps. We don't need all the piping connections for those pumps. And the annual energy cost goes down. So like reducing the flow rates and increasing the delta T's, we can reduce both the install costs and the operating costs. And they published that in a paper. And one of the great parts about that paper, they also talked to the building operators and talk to the consulting engineers who design the systems to find out what are the things you should really know about variable primary flow systems. And from a high level standpoint, the biggest things are, first, you need to stay within the limits of that the chiller provider tells you. That is between the minimum flow rate and the maximum flow rate. If we go above the chiller's maximum flow rate, we can erode the tubes. The chiller will fail earlier. It won't be as reliable for as many years. And also those tubes can actually vibrate and cause acoustical issues. If we go below the minimum flow rate, as I said, our efficiency gets bad, our heat transfer gets bad, and actually we can reduce the suction temperature and pressure in the evaporator so far because the approach temperature gets bad that sometimes in the past people have done it poorly, and years ago, decades ago, they froze the tubes in their chillers. We know how to take care of that today. The second thing is the chiller unit controls need to be able to respond to flow rate changes. So if you're going to do variable primary flow, particularly on an existing chiller, contact the chiller provider to make sure that his or her chiller can operate at different flow rates. And you want to know how fast can the flow rate change. So those two are very important from the product standpoint. Then you always have to have a way to ensure the minimum flow rate. Most of the time that minimum flow rate is done using a separate bypass line and valve. On small jobs, it could be 3-way valves in the system to maintain the flow rate. But those aren't the hardest parts about a variable primary flow system. Here is the more complex part. Again, system controls take care of this, but we have to consider it. And that is, in this system, when we turn an additional chiller on because the cooling load has gone up, nothing changes from the pumping standpoint, because the pumps are still responding to what is the flow rate that the system and the coils need. So from that standpoint, the only thing that happens to turn that second chiller on is we open the isolation valve on that second chiller, it proves flow, and that chiller can now turn on. But when we open this isolation valve, what happens to the flow rate through the chiller that's operating? It drops. And the question is by how much? Well, it drops by 50% if the chillers are identical. The final question is, how fast does it drop by 50%? So the capacity of the chiller is proportional to the flow rate times the delta T. We reduce the flow rate by 50%, the chiller is operating a particular load, the delta T doubles. And depending on the conditions, it could approach freezing, but the chiller has safeties. If it approaches freezing, the chiller will cut off, it will turn the chiller off. But we don't want the chiller to turn off. In fact, in 1994, at an auto manufacturing plant, we were there, and this is exactly what happened. The chiller unit controls weren't as sophisticated, and when we attempted to turn the second chiller on, the first chiller turned off. And the owner, the auto manufacturer, said, let me understand this. We needed more cooling, so you turned all of my chillers off. That's not good, because I'm not now satisfying my manufacturing process. So in that case, what we had to do, we had to slow down how fast the isolation valve opens. In fact, Jim Kreutzmann, who was a consulting engineer, probably did more variable primary flow systems during his career than people who were operating at that time. He wrote articles that said the way you do this is to slow down and open that isolation valve in 2 to 3 minutes. Don't open it in 8 seconds like we did at the auto manufacturing plant. When we slowed down that valve and opened it in 3 minutes, we were able to operate the system properly. And we've figured out how to do variable primary flow systems. They've been used for about 25 years now. So they're different, but they're very doable today. And we're seeing them, a lot of them used because, again, the installed costs and operating costs both go down. One thing we like to share when we give presentations is what is not a good variable primary flow application. And this is, we have 2 package chillers. I kind of separate chillers into 2 different categories. One is centrifugal chillers are customized. The chiller is chosen for the job. The scroll and screw chillers are, they're more of them manufactured, and therefore chiller providers have fewer options. And they're more packaged is what we call them. So in this case, the minimum flow rate is about 0.02 liters per second per kilowatt of refrigeration. The chillers are piped in parallel, and the designer is using a 10 degrees C delta T, 18 degrees Fahrenheit at 10 degrees C. That flow rate is 0.024 liters per second per kilowatt. Well, that means that we can't turn the flow down more than 10%. So this isn't a good variable primary flow option. What could we do in this case? Another thing we could do, we could consider piping the chillers in parallel, in series. When we pipe the chillers in series, we would want to have some bypass lines with manual valves so that if one chiller is being serviced, we don't lose both chillers. We still have the 50% capability. When we do this, we now have a larger pressure drop since we're pumping through 2 evaporators. So we have to be more cognizant of the pressure drops and the flow rates. This works better when we have a delta T of at least 8 degrees C. If we only have a delta T of 6 or 7 degrees C, the pressure drops will be too large, our pump power will be too large, and we will use more power in our system. But once we get to an 8 to 10 degrees C delta T and larger, we can reduce those pressure drops. Another thing that happens in the system is this upstream chiller operates at an elevated temperature. It isn't making the system supply water temperature. That chiller becomes more efficient, and that offsets any increase in pumping energy and pumping power. So this upstream chiller offsetting the pump power increase is wonderful. But what I like best about this system is we talked about in a variable primary flow system, the hardest part is transitioning from 1 to 2 chillers when the chillers are in parallel, because the flow rate through the operating chiller goes down by 50%. When we put the chillers in series and turn that second chiller on, there is 0 flow rate transition. We got rid of the hardest part of a variable primary flow system by mixing the lower flow rates, higher delta T, and variable primary flow, and then putting them in series. This is ideal. If you have an application where you're going to have 2 chillers, the system's unlikely to expand. You're going to a higher than 8 degrees C delta T, and you want to do variable primary flow, really consider putting the chillers in series. It provides great benefits for the building owner. It simplifies things, and it takes you and the building owner away from the hardest part of variable primary flow system, since there is 0 flow rate transition when we bring that second chiller online. So when we're doing this, when we're using the new technologies that are available, we want to provide simple solutions, because simple solutions are reliable. They keep working for years. And when we provide those elegant solutions, we also provide value for the building owner by doing this. The final thing we're going to talk about today before we go to our question and answer is system control. And this can be another 60 to 90 minute seminar, but we're just going to take a few minutes to talk about the most used system controls. In a normal performance chilled water system, most chilled water pumps, distribution pumps are controlled by having a differential pressure sensor at, quote, the most remote air handler, at a valve somewhere out in the system. And as the valves change, the pressure changes, and we modulate the pump speed to maintain the pressure at that most distant coil. The cooling tower fans are often controlled to make the coldest tower water temperature possible. Now, in a climate like yours, where the wet bulbs are high all the time, that isn't as low as in a climate like mine. I'm in Wisconsin. Our wet bulbs are much lower than your wet bulb temperatures, particularly when it's not during the summer. And we can get cooler tower water temperatures. And then we often have constant volume, constant flow condenser water pumps. Let's look at some options. And the first thing we're going to talk about is what's called pump pressure optimization. In pump pressure optimization, we have a communicating building automation system or chiller plant control system that's communicating with the control valves. We get the signal from the control valves, and the signal we're looking for from the control valves is how wide open are you? Because if all the control valves are closed, what's happening is we're putting energy into the pump's producing pressure, and the valves are closing to reduce that pressure. Well, when we get the signal from those valves, we can then change the pressure that the pump is operating at. When we change the pressure that pump is operating at, we do it to maintain the most open valve nearly wide open. So let's look at an example of that. And this is the automation system is taking the feedback from all the valves, and what we're looking for is which valve is the most wide open, because that's the one that's requiring the highest pressure. And if that most wide open, that critical valve is between 75 and 85% open, we are operating in a good position. However, if that valve, that most critical valve, goes below 75% open, now we're putting power into the pump, it's producing pressure, and the valves are eating up that pressure. Why do we want to do that? Well, we didn't have the capability to do this in the past. But now that we know that critical valve position, we reduce the pump static pressure set point, the pump slows down, its power goes down, the pressure goes down, and that valve comes back into this dead band that we want. We're using less pump power. Now, what happens if that critical valve goes above 85% open? Well, if it goes above 85% open, we're in danger of losing the load, losing the leaving air temperature, not providing the cooling necessary for the process. So we will, if that critical valve goes above 85% open, we increase the pump static pressure set point till we satisfy that valve, get it back within this dead band. And what we've done, we've only put the amount of power we need into that pump to satisfy the worst case load. Now, another thing this does is, in the past, we used to have to guess, where do we put the differential pressure sensor? Where's the most remote air handler? Now we can actually have the DP sensor in the plant and reset it on the critical valve position. We don't have to guess, because in the morning, the critical zone and valve will be on the east side of the building. In the afternoon, it will be on the west side of the building. The automation system, the technology changes and optimizes the system for us at every point during the day. The last thing we'll talk about is chiller tower optimization. That is, many people want to reduce the tower water temperature to reduce the chiller power, because what connects the chiller and the cooling tower are what's the water temperature. The tower will produce the water temperature based on the wet bulb, the heat rejection load, and its design. The chiller's power will change depending on its design, its load, but the one that connects these two is the leaving tower temperature, which is the entering condenser water temperature. And the question is, how do we control that? Do we leave it at the design conditions of 29 or 30 degrees C? Do we drive the tower water temperature down when the wet bulb's lower to 13 degrees C? Do we optimize it? This is a graph of a chiller operating at part load condition, 60%, at a particular wet bulb temperature. And at this wet bulb temperature, if we drive the cooling tower fans as hard as possible, the cooling tower can make 23.5 degrees C water temperature, and here's the chiller's energy usage. As we reduce the tower fan speed, its power goes down with about the cube of its speed. So as it goes to 26.5 degrees C leaving temperature, the chiller power goes up, but what we're looking for is, where is the sum of the chiller plus cooling tower energy at its minimum. And that temperature changes depending on what the wet bulb temperature and what the heat rejection is. Now, I will say, I just heard some thunder. I have a direct line for my internet connection, but if there are any issues with that, we have some weather going through at this point in time. So I'll try to go through. A lot of people have looked at this. A person I went to graduate school, Jim Braun, worked for another company in our industry. He found a way to do it. The next three, Heidemann, Gillespie, and Cameron, worked for an electric utility. We published Ashrae Journal articles. Hugh Crowther worked for another chiller provider, Jim Furlong with a cooling tower manufacturer, Mark Kasia with a controls provider in our industry, and these are two different chiller manufacturers work together. All of these different people found ways to optimize the leaving tower set point to optimize the chiller plus the tower, so you can get competitive bids. In addition, Hugh Crowther in his article looked at different operating temperatures in different locations. And as we get to more humid climates like India, the savings available between trying to make the coldest tower water temperature possible and finding optimized can be between, and I've seen between 8 and 15% savings of your chiller plus tower energy usage just by finding that optimal set point. What we have to remember again, however, is the building owner pays for the entire system. The meter is on the building. It's the chiller plus the tower energy consumption. The chiller power and energy goes up, but that's not what matters. What matters is the system energy consumption. Finding near optimal, we need to know what's the tower design. What type of chiller do we have? That line I showed on the graph, that changes. Is it a centrifugal? Is it a scroll chiller? Does it have a variable speed drive? So that changes. But then the two variables are, all we need to know is what is the chiller load and what's the outside air wet bulb temperature, and that optimal temperature can be calculated. So our lesson here is without controls, it isn't a system. So today we covered a number of things. We covered them quickly. There are references available, and I'll answer questions in just a couple minutes. So we talked about first, let's reduce the flow rates. Let's use the Ashrae GreenGuide recommendations to make our systems more efficient and more cost effective. Let's consider doing the same by using variable primary flow systems. Then, when we look at variable primary flow systems, we can also install them in both new and existing applications. And from a system control, we talked about pump pressure optimization and chiller tower optimization. Now in 45 or 50 minutes, we can't cover all of the questions that you have, but hopefully we'll be able to cover some. So I'd like to leave you with these thoughts. First, again, well, controls, it's not a system. It's just a bunch of different pieces trying to work, but there needs to be an integration. A chiller plant control system, a building automation system needs to coordinate and control the plant so we can make it simple, we can make it elegant, we can make it reliable and efficient. That's extremely important. Next, we always have to remember what the building owner pays for and basically what our impact on the environment is. As we reduce the energy usage of the system, of the building, we also reduce our emissions. We reduce the energy created at the power plant, the energy inputs to that power plant. Finally, I like to share when our oldest son, he's now 33 years old, when he was 5, he looked at me and said, "Daddy, what do you do?" I do chillers, I chilled water systems, I help, oh boy, how do you explain that to a 5-year-old? And I thought about it a little while, and like you, I solve puzzles. As consulting engineers, as project teams, as building owners, as operators, as contractors, we get to solve puzzles every day. We get to reduce the energy intensity of the world. We get to reduce the emissions. We get to make things better all day, every day. We have the best jobs in the world. We get to help people. Think of living in your environment without what Dr. Carrier and Mr. Trane did. They founded an industry. Think of what we are doing with today's technology that President Gulledge is talking about, using that technology to make the systems better, to make them operate better. You have an extremely large impact on the industry and on our environment. Thank you for all that you do. With that, again, this is a distinguished lecturer program. We hope that you'll provide feedback to us, and Money will move into the question and answer session. I can stop sharing my screen if you'd like, and please unmute your microphone, and let's see what questions we can answer.
Hi, Mick. This is Mihir Sanghvi. I'm president of Ashrae Mumbai chapter. How are you doing?
I'm well. Thank you so much for hosting us today.
No, indeed a pleasure. You have indeed solved a lot of puzzle for all the members of Ashrae Mumbai chapter, Chandigarh chapter, and Falcon chapter. I mean, the kind of presentation is simply amazing, and we have close to around 700 delegates still online. Shows that, I mean, the kind of quality program what you gave as a TL. So simply superb. That is the first feedback what I can give you, Mick. So I have tons and tons of questions. So I'll start with the first question. Please provide the COP requirement at high ambient temperature of 50 degrees Celsius, possible applicable correction factors which are required for HRI, which considers 35 degrees as ambient.
Sure. Okay, so for screw and scroll chillers, the COP required is the same because they're the same pieces of equipment. They will use more power at those higher conditions. How much more depends on the specific compressor type. But I will say in the range, I hate to give rules of thumb because then people use them. It's best to work with the chiller provider to get the actual data, because then you'll make the best decision. But I will say between 1 to 1.5%, pardon me, let's do degree C. 2% per degree C increase in chiller power would be a decent rule of thumb. On centrifugal chillers, the compressors actually change on a new job, and you would select a different chiller with a higher pressure difference. Therefore, the COP goes down, but the important part is the COP goes down, the chiller power goes up, but the important part is the system power goes down. And we need to make sure that we are always looking at the system. The chiller power goes up, but its COP is still between, maybe its COP goes from 7 to 6.5. It's still close to 10% more efficient than the COP of a pump.
Thank you, Mick. I hope Mr. Syed Shoaib ur Rahman, your question was answered. The next question is from Mr. Sandeep Dahiya. Won't the scaling tendency increase at higher condenser water entering temperature with high delta T on condenser?
Okay, great question. And the answer is there was a study done on scaling by a person at Penn State University. And he found that as long as we stay above the minimum flow rates, there is not an increase in scaling. Now, there may be some locations where the water quality is not as large. In the United States, New Mexico has poor water quality, and I know in working on some jobs, there's some locations in India where the water quality isn't as good. Just because the flow rate goes down doesn't mean the water velocity in the tubes goes down. You can still select the number of tubes for that condition to keep the water velocity up. And it's really the water velocity that can, if it gets too low for too long a period of time, can lead to increased scaling. But you can work with a chiller provider to select those chillers at the same water velocity, and then there's no difference at all in scaling. Great question.
Yeah. The next question is from Mr. Hamza Fada. The running time for the chiller will be less and save energy when increased delta T?
Not necessarily. The chiller's job is still to satisfy the cooling load. And as long as its capacity is still the same and the cooling load is still the same, the chiller itself will have the same amount of runtime because it still has to satisfy the same load. Now, so the delta T really doesn't affect the running time of the chiller. But one thing that can affect the running time of the chiller is if, let's say you have a job where the chiller cycles and the chiller cycles more than you like. What you can do, the chiller will have on its unit control panel has what's called a differential to start and a differential to stop. So if we're trying to make 5 degrees C leaving water temperature, the differential to stop might be 1 degree. That is, until the water temperature gets down to 4 degrees C, it won't cycle off. And then the differential to start would be the 5 degrees C plus say 2 degrees C. So until the loop gets up to 7 degrees C, the chiller doesn't start again. So while in the lower delta T or the higher delta T doesn't change the running time of the chiller, you can, if the chiller is cycling, use the differential to start and stop to get the chiller to cycle less and fewer times.
Thank you for a great answer. The next again question is very nice question that is there from Mr. Sandeep Daya. Why do we not have fouling factors for cooling towers and air-cooled chiller condensers? Fouling of these equipments increase energy consumption, but there are no recommendations from HRI or Ashrae for this. What is your opinion about that?
My opinion about that sounds like a great research topic.
Absolutely.
And Anuj talked about funding research. And I will say that Ashrae research funding is continuing. It's continuing at the same level that it was before the pandemic hit. So we're working very hard to do that. But if that would be great research to bring to our technical committees, and if people would want to donate to that research, Ashrae is one of the few societies that funds its own research. And the benefit of that is we don't have to get to any particular answer. Sometimes when research gets funded by a particular company or a particular entity, they want a particular answer. And I'm not saying the researchers try to get there, but there is pressure. With Ashrae, the research is the research. So I think that this would be a great research topic. And I'm going to write that down here real quickly. Let's go to the next question.
Right. I think the next is not a question, but it's more of a statement by Mr. Muhammad Abdul Wahab. The larger delta T, the large delta T, the larger cooling coils for building, and hence the more fan power use.
That all depends. There are two different ways to do the larger delta T. One is to make the coil bigger and use the same inlet chilled water temperature to that coil. The second is to use the same cooling coil with the same air pressure drop and the same fan power and give that coil colder inlet water temperature. And I will say in most applications, we're seeing on new jobs, people using similar coils, but colder chilled water temperature because the COP of the chillers has gone up so much, and we don't want the fan power to rise. And by using colder inlet water temperature, we often can use the same cooling coil and not have any effect on the fan power. So thank you for bringing that up.
Thank you, Mick. Again, a brilliant question by Mr. Sandeep Daya. I think you have a lot of research topics coming up from him. If the design coil water velocity was 1.5 FPS, won't the water velocity fall below 1 FPS and make the flow laminar? Ashrae says coil performance is uncertain for velocity less than 1 FPS. Is this not an issue? At lower loads, water velocity will fall further. If not at design, the coil won't give desired delta T at low loads. Is this not correct?
Great question. Absolutely great question. Actually, I don't know. I don't think there's research that needs to be done on this because this is a non-commercial thing. The group that I work for produces non-commercial literature that actually has gone through and looked at what happens with coil selections, what happens with existing coils. When we think back to our textbooks, we think back to turbulent flow and laminar flow, but our textbooks always use straight pipe. A coil isn't a straight pipe. And in that coil, we have a lot of U-bends, and those U-bends tend to help keep the heat transfer up. But the questioner is exactly correct. At some point, we get a reduction in heat transfer. So we want to make sure we work with the coil provider to provide the circuiting so that we don't reach those points. There are also some internal enhancements, they're called turbulators, that work extremely well to keep the flow rate turbulent and the heat transfer high, even at low flow rates. So yes, this is something we should be aware of. There are materials available to help explain where we need to stay from a turbulent flow standpoint. But when we look at the heat transfer of coils, it doesn't drop off the cliff like our textbook showed. There's a difference in heat transfer when we go through that transition from turbulent to laminar, but the heat transfer doesn't go nearly to zero like our textbook shown. But we do need to be aware of it. So thank you for asking and bringing that up.
Great. This will be the last question due to the paucity of time. It is by Mr. Farooq Ahmad. What is the effect on coil leaving air temperature with higher delta T?
In the case that we showed, there was no effect on coil leaving air temperature. We wanted to have the coil leaving air temperature exactly the same. Now, when I say exactly the same, when we did the selections that I showed you, the leaving air dry bulb was the same. But I will say that the leaving wet bulb went down by 3/100ths of a degree, which in my world, that's the same. I can't measure that. So when we reselect the inlet water temperature to maintain the same leaving air temperature, both the dry bulb and the wet bulb are almost exactly the same. Now, we could, in a retrofit application, give a coil the same amount of water and colder water, decrease the leaving air temperature, both dry bulb and wet bulb, and get more capacity out of that coil. But we don't have to. We can have the same leaving air conditions, both dry bulb and wet bulb, using different inlet water temperatures.
Mick, thank you so much. I would have loved to end this with this is last question, but there is one specific question by Mr. Hassan Yunus, and this would be the full and final last question for today's webinar. What's your take on chill water thermal storage with variable primary versus chill water thermal storage with constant primary and variable secondary?
That really good question. And before I answer the question, I just want to say thank you to everybody who came today. Thank you to the chapters, the sponsors. Thank you also to RADA as your sponsors. It's been wonderful to be with you virtually. I hope sometime in the future it will be face-to-face. Now, could you please, after I said the thank you, I forgot what the question was.
I'll repeat the question for you, Mick. What's your take on chill water thermal storage?
Okay.
Yeah.
So thank you. Chilled water thermal storage can work both either in a variable primary flow system or in a primary secondary system. It's all about how do we do the pumping and how do we maintain proper stratification in the chilled water storage tank. We don't want a well-mixed tank. The density of water is at its maximum between about 3 and 4 degrees C, 39 degrees Fahrenheit. And we want to store that 39 degrees C water in the bottom of the tank, and we want to have a thermocline. That is, we want to have as much 39 degree water as we can in that tank. When we're putting water into and out of a tank, we need to make sure if it's not baffled, it comes in slowly so the water doesn't mix. We keep the thermocline. I will say that some people find it's simpler to hydronically pump the system when we have 2 sets of pumps with a storage tank. But I have seen it used in variable primary flow system, chilled water thermal energy storage. One more thing. We can do variable primary, variable flow too. It's variable primary, variable secondary with 2 sets of pumps. And that can, we don't get the same first cost savings, but we get some good operating cost savings and flexibility.
Thank you so much, Mick. There are at least 20 to 30 more questions, but due to paucity of time, we apologize to all the attendees. We won't be able to take them live, but we'll sure forward your questions to Mick, and I'm sure I think you can forward. Over to you, Mani. And thank you so much. It was a pleasure listening to you, Mick.
Thank you.
Yeah, thank you very much, Mr. Mihir, for taking this session for the question answer session. And thank you, Mr. Mick, for your great support and for your time and sharing the session and insightful information. I must say that was actually insightful information that you have shared with all the attendees. And once again, I would like to thank you for all of your participation. And we are so grateful for all of your support. And I must say, without you, this wouldn't be possible. And keep participating and learning with Ashrae. See you there. Our next webinar is on 7th of August, which is on design, build, operate, and maintain. What could possibly go wrong? So that would be deliberated by Mr. Chuck Galich, who is Ashrae president this year. And yes, at the end, if you are not a member of Ashrae, I must encourage and motivate all of you to please join Ashrae and get more insightful information that are being deliberated in the form by the webinars and the education, Ashrae Learning Institute, and many technical groups and committees which are available in Ashrae, where you can be a part and contribute. At the end, again, would like to thank you on behalf of Ashrae Chandigarh chapter, Ashrae Falcon chapter, Ashrae Mumbai chapter, and RATA the Refrigeration and Air Conditioning Traders Association. I again thank you very much for all of your time and participate in this webinar today. Thank you very much, and I'm sure we are signing off.